Hello, my name is Nakib. I'm going to present my work with Boris Kozinski on the electron-phonon drag enhancement of transport properties from a fully ab initio Boltzmann formalism. I'm going to begin with a very brief introduction to the problem of transporting the interacting electron-phonon gas. So in the typical approach, one solves a decoupled Boltzmann transport equation, or BTE. So when one solves the electron BTE, they take the phonons to remain in equilibrium. And when they solve the phonon BTE, they take the electrons to remain in equilibrium. This way, what happens is one cannot fully capture the interspecies exchange of momentum. So this means that they will not be capturing the drag effect, and also they might end up sometimes severely underestimating some of the transport properties, transport coefficients. So in our approach, we solve a coupled set of BTEs. This way we capture the phonon drag effect. So the phonon drag effect happens when phonons move with electrons, reducing the momentum dissipation of the electronic system and boosting the electronic transport coefficients. We also captured the electron drag, which happens when electrons move with the phonons, reducing the momentum dissipation of the phonon system and boosting the phonon transport coefficients. And these two effects kind of go together. You cannot separate the two in any meaningful way. So another thing is this electron-phonon drag effect is supposed to be typically thought to be a low temperature effect. But in this work, we show that electron-phonon drag can be exceptionally strong, even at room temperature for cubic silicon carbide. So the coupled set of electron-phonon BTEs can be presented schematically as shown here. So the field that will couple to your particles will pump momentum into the system, so into the phonon system or the electron system or both. And the phonon and the electron systems can exchange momentum via these electron-phonon and phonon-electron interaction mechanisms. They can also lose momentum via dissipative channels such as impurity scattering, club phonon-phonon scattering, or phonon isotope scattering, etc. So mathematically, you could write down these BTEs in the form of these response functions to this applied temperature gradient field or the electric field. So the details of what goes on into these functionals are given in these two papers, and I invite you to read those if you're interested. But I will zoom into just the temperature gradient set of equations to give you an idea of what each of these terms means. So if you restrict yourself to just the first term of these two equations, then you would be first decoupled. You'd have two decoupled equations, and you would be in what is known as the relaxation time approximation, or RTA. So the RTA involves evaluating this kind of elementary scattering processes and then forming scattering rates. So electron-phonon scattering and phonon-phonon scattering, this will go into this RTA terms. But after that, that's it. There's no equations to solve per se. So this way, you're going to be missing out on something called the in-scattering correction, which can be important in many materials. And two, you will not be capturing any drag effect. Now, you can do better than that by adding this second term. You'd still be decoupled, so there will be no drag effect, but you'll be adding in the in-scattering corrections. And this seems to be a standard. It has become a standard nowadays to be able to solve the BTEs at this level. So for electronic BTEs, you can use the EPW code or the perturbo code to calculate the BTE at this level. And for the phonon BTEs at this level, you can use the Sheng BTE, ELMA BTE, phonon 3pi, and there are many other codes that I'm not listing here. But if you want to capture the drag effect, then of course you have to add this last term, and this last term, these last terms will couple these two equations completely, and now you need to solve these two equations self-consistently. And once you do that, you get both the in-scattering corrections and also the drag effect. So we build this and implemented this methodology, and we applied it to cubic silicon carbide. So cubic silicon carbide is a zinc blende structure. It is a polar material. We will be interested in n-doping the material only, so we have just one transport active electronic band here. The phonon dispersions are shown on the right here. The elementary phonon-phonon and electron-phonon scattering matrix elements are calculated ab initio, and then we just plug all of these quantities into our BTs and solve them. So before showing you the transport coefficients, I want to show you the electron RTS scattering rates. These are important for us. It's important to look at these because these help explain how electrons like to interact with what kind of particles in the system. So on the left, the electronic scattering rates are given for 10 to the 16 per centimeter cubed. On the right, for 10 to the 20 per centimeter cubed, doping concentrations. First, note that there is a large longitudinal optic phonon energy scale, or LO energy scale, and that there is strong acoustic phonon scattering. The high LO phonon energy scale means that the LO phonon emission onset happens at a higher energy for the low concentration case. And for the high concentration case, this means that the LO phonon scattering rates will dip significantly near the chemical potential. So combine that with the fact that electron acoustic phonon scattering in this material is strong. That means that electron acoustic phonon scattering will dominate in both these two cases at 300 Kelvin. So the momentum pumping of the low energy acoustic phonons will be guaranteed. Now let's look at the phonon RTA scattering rates. First, note that phonon-phonon scattering will mix momentum among the phonons, and phonon-electron scattering rates will send momentum back to the electrons. So we see that for low wave vector or low Q phonons, these suffer fewer Umklapp scattering, so they tend to be long-lived. So if these phonons receive momentum from the electrons, then they'll be able to hold on to this momentum. Next, note that phonon electron scattering rates, shown in red here, is higher than phonon-phonon scattering rates in the high doping case. So these phonons, low wave vector phonons, will be able to send back this momentum to the electrons, forming this momentum loop between the electron and the phonon systems. Similarly, for the high doping case, zone center longitudinal optic and zone boundary longitudinal acoustic phonons will also be strongly drag active. Now let's look at a couple of the transport coefficients. For time restriction, I'll just look at two. First, the electron mobility. We see that there is strong phonon drag gain in the absence of electron impurity scattering. So there is this 191% drag gain for the 10 to the 20 per centimeter cube doping. This happens because of this robust momentum feedback loop that happens between these phonon and electron systems. If, however, you turn on electron impurity scattering, that is, open this valve right here, then momentum destroying electron impurity scattering will be dominant, and this drag effect will be weakened. So we have a message for the experimentalists. If you want to exploit this drag gain of mobility, you have to introduce charged carriers without introducing charged impurities. Next up, I'm going to look at the thermopower, and I'm going to discuss this in the Zebek picture. There is very strong phonon drag contribution to the thermopower at the low doping limit. So these green curves right here are higher than these blue curves, which are the electronic contributions. So this happens because low energy phonons are strongly drag active, as I've shown before. What happens is the rate of momentum transfer to the electrons is linear in electron doping concentration in the low doping limit. So at the same time, there's fewer electrons in the system. So the momentum received per electron is still large and a constant, which is why this green curve is saturating to a constant value at low concentrations. Interesting fact is that finding is that the phonon drag thermopower is immune to the presence of impurities in the system. So the way this happens is as follows. So the rate of momentum transfer from the electrons to the system, electronic system, remains the same as before, even when you open the electron impurity scattering channel. Now, the electrons will lose some of this momentum to the impurity channel, but the per electron momentum gain from the phonons will remain the same as before because of this open circuit condition of the Seebeck setup. So in the end, the same steady state Seebeck voltage will develop and you'll have the same large phonon drag gain of the thermal power. So another message to the experimentalists is that you should be able to see this in action. So if you do Seebeck measurements on samples with different amounts of impurities, you should still get the same thermal power. So I'm going to quickly summarize. We developed here an ab initio coupled electron-phonon Boltzmann transport equation solver, and to my knowledge, this is the first of its kind. We applied this to cubic silicon carbide and showed that there is very strong drag enhancement of a couple of transport coefficients, even at 300 Kelvin. One, the phonon drag boost of the mobility is strong, and this can be exploited if charge carriers can be introduced into the system without introducing charged impurities. And two, there is an exceptionally strong drag boost of the thermal power, which seems to be robust against impurities. Thank you.